prime, if you have an extension of Q, which is normal, and discriminant D, and you define just notationally compositum, but for finite, this has a lot of conditions to it. All right. You also have some other K over Q, which is a finite normal extension. And C is a union of conjugacy classes all right, almost there. So then you have S is the set of primes such that its Artin symbol is in C, and P doesn't split in FL for all L. So this should look familiar, right? The idea here is that we have the primes that behave a certain way in K, but don't split completely up into L. We need more conjecture. I'm going to go this way. Because there's space here and I want to keep it on one board. Explicitly computes what these FLs are. And I think, although I haven't checked, I think that's where it's going to end up being very hard to keep track of all the composita and roots and what's going on. In general, I think you could. I think this could be generalized. And I was talking to Hans Roscom, and he said that somebody had done some generality, but he wasn't sure of the most recent stuff. Yes.
Maybe this is silly, but why are we working? Oh, never mind. I get it. We're good. Okay.
Sure.
Yeah.
And Murdy assumes GRH?
Murdy, that's a good question. I didn't think so. But, oh, yes, he also assumes GRH. Yeah, he needs GRH for all the FNs. That's right. Idea. And simply, without proof, write down what these extensions are so that you can see them and then so these FLs that are encoding whether or not something is in a prime is in SL or not. Again, we're checking if the prime splits completely there. So there's cases depending on 2 or not. And so this is for the split primes. Plus means split. These are the extensions you have to look at, and you have to check whether the primes split completely there or not. And again, and you can explicitly compute what the degree of this extension over Q is, so you can explicitly compute the density of primes which split completely. This takes a page of work. Not a lot, but not completely non-trivial, but not hard. For the inert primes, it gets complicated to explicitly write down the extensions. Well, I said I would do it. The last case is complicated. it's defined as the fixed field of a specific part of the Galois extension of something. So, but it's easy to write down the compositum of k with fn minus. So I'll write that down because that one's nice and easy. This is always k adjoint zeta n through to phi. So it's very easy to get your hands around this. And for split, it's similarly easy. So once you have this stuff, and this takes a little bit of work to prove that these are the right extensions, but it's similar to the Artin's proof stuff. Then you have to do a little bit of work to calculate what the degree extension of Q is, and then apply Raup-Murty's theorem and show that you can do your inclusion and exclusion in the limit. So I think I'm going to stop here. Any questions? Yes, Hunter.
So this stuff that Hester has been doing with like is OK cross to OK mod P cross surjective, which I guess is a little coarser of a question. Is it the same techniques? Are y'all like working on this together?
I've never spoken with Hester about.
Oh, okay.
So I don't know how Hester's doing it, but
should be related.
But it should be related, and even more so since she's working with Raup-Murty on it.
Yeah.
I imagine it's quite related.
I think, yeah, people have been using the Artin's conjecture to prove rings are Euclidean
Okay.
for 30 years.
And it's like how she rolls. Okay, that makes sense.
I imagine that's what she's doing, but I don't know that for a fact. Anyone else? Okay. Cookies and tea.
Oh,